Hello, this is Deborah Barrett with the Cincinnati State Physics Department presenting a sample problem from Chapter 8. I would like to suggest that before you work your way through this problem, you pull out your notes from the prior video comparing translation and rotation. The problem statement is given on screen. After listening to some old Beatles LPs, a vintage music enthusiast decides to go seriously retro and put on a Duke Ellington record. While the turntable is coming up to speed, 33 RPM to 78 RPM, it turns 4 1/4 times. What is the turntable's acceleration? We'll be using risers for this problem, so we're going to want to imagine this, which you can probably all imagine this, and then we're going to make a sketch. So here's my sketch of the turntable. And I'm going to use a motion arrow to represent it turning. Next, with risers, after sketching, we equate, which is to label the sketch with tiny information equations. My first piece of information is that the turntable starts this problem at 33 RPM, which is the speed for an LP. So in order to decide what I should be calling this, here's a typed up version of the rotation versus translation sheet from the prior video. As you can see, we have at the very top, translation is motion along a path and rotation is spin. Well, if we're talking about throwing the record player or the turntable across the room, then we would be dealing with motion along a path. But instead, we are talking about the turntable turning. So we are looking at a rotation, which means that the section that we want to look at is in the lower right. We have in the upper right the definitions for the different rotational concepts, and we see that angular velocity, which would be how fast the object spins, would be symbolized with the lowercase omega. So I'm going to symbolize this with lowercase omega, and I'll use a subscript 0 to represent that this was at the start of the problem. Similarly, the final speed is 78 RPM, and that will again be an angular velocity. So I will mark that at the end of the motion arrow. We also have that the turntable turns 4 1/2 times. How many times it turns would be telling the angular displacement, and from our reference sheet we can see that that would be a delta theta, the change in its position. Delta theta is equal to 4.25 revolutions. Now, the problem asks, what is the turntable's acceleration? If you look again at your summary sheet comparing rotation and translation, you see that for an angular acceleration, the symbol is alpha. So we are looking for alpha, and I will mark that with a question mark to help keep me anchored. Okay, so we're in risers, we've done the RISE. Now it's time to choose a relationship. We definitely want a relationship with alpha in it, since that's the unknown. So let's go back to the reference sheet. What I often do when I'm working something like this is choose which of the equations have the unknown I'm looking for in them, and then go on from there. Well, we have an alpha right here, so this would be a candidate that we could consider for this problem. We also have an alpha right here, so here's another candidate we can consider for this problem. This equation also has an alpha in it, so here's another one we can consider for this problem. And then finally, our last equation does not have alpha in it, so that's not an obvious terrific choice. Next, we want to look at whether these equations have in them, or call for, information that we have available in the sketch. This first equation calls for final velocity and original velocity, which we have, but it also calls for time, which we do not know. So that's not such a great choice. The second equation calls for delta theta, that's the angular displacement. We do have that. You'll remember the angular displacement was 4 1/4 revolutions. It also calls for the original velocity, which we have. That was given as 33 RPM, but then it calls for time, and we don't know the time. So if we want to do this problem with just one equation, once again, this is not the best choice. Going to the next equation, we have a need for the final velocity, which we know the final angular velocity is 78 RPM. The equation also calls for starting angular velocity, which we know that was the 33 RPM. It calls for alpha, which that's our featured performer. That's what we're looking for, so that's fine. And then it calls for delta theta, which we do know because we were told 4 1/4 revs. That means that if we choose this equation, we can work the whole problem with one equation. And I got to tell you, I'm all for that. So let's bring this equation to our page to go on. So here's the equation we just chose. Final angular velocity squared will equal starting angular velocity squared plus 2 times the acceleration times the displacement. Now let's see. We want to find alpha, so let's rearrange this to solve. I'm going to subtract the omega 0 squared from both sides of the equation. So that'll be omega final squared minus omega 0 squared equals 2 alpha delta theta. And then I need to divide both sides by the 2 and the delta theta in order to get alpha alone on one side of the equation. So let's divide by 2 delta theta on both sides. And I think I'll go ahead and rearrange it into the standard format where we lead with the unknown. So I'm going to rewrite it as alpha equals omega final squared minus omega original squared divided by 2 delta theta. Now I'm ready to start filling in the information from the problem. For omega final, we have 78 RPM. At the point when you're starting to fill in the information in an equation, I recommend that you always put any fractional units written vertically instead of horizontally. So I'm going to call this 78 revolutions over minute, and since it needs to be squared, I'm going to show it squared. Then I have my subtraction, and then the starting angular velocity, which is 33 RPM. And again, I'm going to put that as revolution per minute written vertically. And then we're going to divide by 2 times delta theta, which was 4 1/4 revolutions. Now, it's a little non-standard to answer an acceleration in revolution per minute, but since I didn't specifically say we had to go standard units in this problem, I'm going to do that exact thing. I'm going to take the 78 squared, and I'm going to take the 33 squared, and then I'm going to subtract those and divide by the 2 times 4.25 revs. I've shifted this over to give me a little more working room. 78 squared is 6,084 with a unit of revolutions squared divided by minute squared. And then we're subtracting 33 squared, which is 1,089 revolution squared per minute squared. and then we're dividing by 2 times 4 1/4, which is 8.5 revolutions. Now when I do the button punching for that, I get 587.65. But you know, I started the problem with just 2 sig figs. So putting down 5 sig figs is really overkill. I've mentioned in class that I'm okay if you carry and present 1 extra sig fig, but we're not going to put down 5. So I'm going to round this off. Instead of 587.65, I'm going to round it off to 588. Now on the units, we're going to have revolutions squared divided by minutes squared in the numerator, and that's being divided by another revolution. So we're going to wind up with revolutions divided by minutes squared as the acceleration of the turntable. One thing I'd like to point out to you is that for our standard work, we will often be taking clockwise as negative and counterclockwise as positive to be consistent with our author, Giancoli, and to be consistent with the way angles are measured, where counterclockwise is taken to be positive. However, when all the information in the problem is clockwise, I think there's not any harm in choosing clockwise as the positive direction, which is what I've done here. Similarly, there's no reason we could not have converted everything over to be radian per second, but since all the information was given in revs, I don't really see an advantage in switching over to radians. So this completes our sample solution of the turntable problem. Thank you for joining me for your physics.